In question 1a, we are told that the absolute value of an expression is equal to 11. The absolute value of a number represents its distance to 0, and there's two numbers which are 11 units away from 0, 11 and minus 11. Each of these cases gives us a linear equation which can then be solved for m. In part B, we need to rearrange a formula to isolate k on one side. We can eliminate the fractions by first multiplying across by j plus k, and then multiplying across by h. Next, we can group the k terms together by subtracting k from both sides. From here, we can factorise out the k, and then divide both sides by h minus 1. Part C involves a cubic expression. Any cubic expression can be written as the product of a quadratic term and a linear term. In this question, we are told that the quadratic term is x squared minus px plus 1. Letting ax plus b represent the unknown linear term, we obtain an equation. Expanding the brackets on the right-hand side produces a cubic expression, and matching the coefficients with the given cubic provides us with 4 equations. The first equation tells us the value of a directly. Subbing this into the second equation and rearranging tells us that b is equal to p. Subbing these values into the third equation gives us the value of p, and then subbing into the fourth equation gives us the value of r. In question 2a, we must use the coordinates of the minimum point to identify two unknown coefficients in a quadratic function. The derivative of a function must equal 0 at a minimum point, so we should differentiate the function and then set it equal to 0. We sub in x equal to 3, since this is the x coordinate of the minimum point. Subtracting 6 from both sides tells us that b is minus 6. We know that 3 minus 1 is a point on the function. This means that if we sub in x equal to 3 into the function expression, we must obtain an answer of minus 1. From here, we can fill in the value of b, minus 6, and then rearrange the equation to solve for c. Part B involves evaluating a limit of a 3-term sum. In the first term, we can divide above and below by n. In the second term, we can split up our fraction. And in the third term, we can distribute the power above and below the line. N divided by n is 1, and n plus 1 divided by n simplifies to 1 plus 1 over n. 1 to the n simplifies to 1. As n tends to infinity, 1 over n, 1000 over n, and 1 over 3 to the n will all go to 0. Computing the resulting sum gives us an answer of 2. In C, we must transform the graph of a function. In part 1, we are subtracting 2 from the value of the function. This corresponds to a shift 2 units downwards. In part 2, we increase the value of the input by 3. This corresponds to a shift 3 units to the left. In question 3a, we can use a proof by contradiction to show that root 2 is not rational. To begin, we assume that root 2 is rational and express it as a fraction of two integers, p and q. we can assume the fraction is written in its simplest form, which implies that p and q have no common factors. Squaring both sides and rearranging tells us that 2q squared equals p squared. The left-hand side has a factor of 2 and hence is divisible by 2. It follows that the right-hand side must be divisible by 2 also. This implies that p is even. If p is even, then the right-hand side, p squared, will be divisible by 4. This means that the left-hand side, 2q squared, will also be divisible by 4. This implies that q is even. P and q both being even means that they have a common factor of 2, and this contradicts our assumption that they don't have any common factors. Part B involves an equation with several log terms. The number in the base of the logs are all powers of 3, so we can use the log rule for changing bases to rewrite each expression so that they have a 3 in the base of the log. Now, every term in our sum has a common factor, log base 3 of t. This can be factored out. Next, we can divide both sides by 1 plus a half plus a third plus a quarter. Calculating the right-hand side tells us that log base 3 of t is equal to 4.8. Raising both sides as a power base 3 tells us that t is equal to 3 to the power of 4.8. In part CI, we can explain the meaning of log base 6 of m as follows. It is the power which 6 must be raised to if you want to obtain an answer of m. In part II, we are told that m is greater than 6 and asked to consider the value of log base 6 of m. Since 6 to the power of 1 is equal to 6, to obtain a value greater than 6, we will need a value greater than 1 in the power. Hence, log base 6 of m must be greater than 1. In question 4a, we are told that 1 plus I is a root of a complex number equation. We must use this to solve for the unknown value of p. To start, we sub in z equals I plus 1 into the equation. Then we can rewrite 1 plus I squared as 1 plus I times 1 plus I. Now we can expand our two pairs of brackets. Next, we combine like terms. Then we can use the fact that I squared is equal to minus 1 and simplify 4 plus 1 to 5. As the final step, we subtract 5 plus 3i from both sides. Part B involves an application of de Moivre's theorem. This requires our numbers to be written in polar form, so the first step is to use our calculator to convert the given complex number into polar form. Our equation involves w squared. To find w, we should square root both sides of the equation. We have to be careful to remember to write in a plus-minus sign here. This is necessary because positive and negative versions of the same number both square to give you the same result. Now we can apply de Moivre's theorem with r equal to 2, theta equal to 120, and n equal to a half. We can simplify, use our calculator, and then multiply in the root 2. To obtain our final answers, we split the plus-minus sign into two separate cases. In part C, the complex number u is equal to a plus bi is plotted on an Argand diagram. In part 1, we must calculate IU and IU conjugate. Since U is equal to A plus BI, IU can be written as I times A plus BI. This expands to AI plus BI squared, and since I squared is equal to minus 1, this can be simplified to AI minus B. Writing the real component first, this becomes minus B plus A times I. To find the conjugate of this number, all we have to do is change the sign of the imaginary component, so the plus AI becomes minus AI. In part 2, we plot these numbers on the Argand diagram. In part 3, we need to send U to IU conjugate. There's 2 steps here. First, we multiply by I, which corresponds to a rotation of 90 degrees anti-clockwise. Then we take a conjugate, and this corresponds to reflecting in the horizontal real axis. In question 5a, we need to differentiate a function which is expressed as a fraction. This requires the quotient rule. We let u be equal to the numerator, which is 1, and we let v be equal to the denominator, which is 5x squared plus 7. Differentiating u tells us that du dx is 0, and differentiating v tells us that dv dx is 10x. We sub these values into the quotient rule statement, and then simplify to get our final answer. In part B, we must evaluate the derivative of a function at pi over 2. The function is written as the product of 2 expressions, so here we should use a product rule. The first term, u, is tan of x over 2, and the second term, v, is ln of x. To find du dx, we must use a chain rule. The inner differentiation gives us 1 over 2, and the outer differentiation gives us secant squared of x over 2. Du dx is found by multiplying these together. dv dx can be obtained directly using a rule from the formula book. ln of x differentiates to 1 over x. Now that we know our derivatives, we can sub into the product rule statement. To evaluate the derivative at pi over 2, we replace each x with pi over 2. From here, we simplify our expression and do some calculator work. C involves functions. In part 1, we must apply f and then g to an input value of 3. F maps 3 to the icon of the world, and then g maps the icon of the world to w, so that's our answer. To solve part 2, we must show that g is injective but not surjective. A function is injective if no output value is mapped to more than once. For the function g, the output values correspond to the set C. Since no output value in C has more than one arrow coming in, g is injective. A function is surjective if every output value is mapped to at least once. Since y has no arrow coming into it, g is not surjective. In question 6a, we are given functions f of x and g of x. In part 1, we must find the 2 values of x where the functions are equal. To solve this, we begin by setting the function definitions equal to each other. Then, we group everything together by subtracting x plus 4 from both sides. We simplify the right-hand side, and then factorise the resulting quadratic. The only way 2 numbers can multiply to 0 is if one of them is equal to 0. So either x minus 3 is 0 or x plus 2 is 0. This gives us two solutions, x equals 3 and x equals minus 2. In part 2, we need to find the area of the shaded region in a diagram. In the given interval, f is always greater than g, so we can obtain the area by integrating f of x minus g of x between the given bounds of minus 1 and 2. F of x minus g of x simplifies down to x minus x squared plus 6. We integrate this expression, sub in the upper bound of 2, sub in the lower bound of minus 1, and then subtract the answers. This gives us a final answer of 33 over 2 square units. In part B, we have an equation involving an integral, and we must solve for the unknown constant b. To begin, let's forget about the limits and focus on the integration. B is a constant, and multiplicative constants can be brought outside the integral sign. Now we can integrate e to the bx using a rule from the formula book. Simplifying gives us an answer of e to the bx. To find the definite integral, we need to sub in the upper limit of b, sub in the lower limit of 0, and then subtract. Simplifying this gives us e to the power of b squared minus 1. We can write this expression in for the integral on the left-hand side of the given equation. From here, we add 1 to both sides, take ln of both sides, and then square root both sides. The question stated that b is positive, so we only want to take the positive solution. In question 7, we are given a function describing Fiona's speed t minutes after passing a point A on the motorway. In part A, we must find her speed when she passes the point A. This occurs at a time of 0 minutes, so all we need to do is sub in t equal to 0 into our function. In part B, we need Fiona's acceleration 5 minutes after passing the point A. Acceleration is the rate of change of speed, so we can obtain the acceleration function by differentiating the speed function. We're working with a time of 5 minutes, so we sub in t equal to 5 to get our answer. In C, we must find the time in the first 4 minutes at which Fiona reaches her maximum speed. Maximum points occur when the derivative is equal to 0. We found our derivative in part B, so we can set this expression equal to 0. We're left with a quadratic expression, and this can be solved using the quadratic formula with a equal to 2, b equal to minus 12, and c equal to 13. We end up with 2 solutions, but only one of them occurs in the first 4 minutes, t equal to 1.42. We can verify that this is indeed a maximum point and not a minimum point by showing that the second derivative is negative at t equals 1.42. In part D, we must use integration to work out Fiona's average speed over the first 5 minutes. To do this, we integrate our speed function between the limits of 0 and 5, and then divide by the length of the interval, which is simply 5 minus 0. Each of the terms in the function can be integrated using the rule of raising the power by 1 and then dividing by the new power. We sub in the upper limit of 5, sub in the lower limit of 0, and then subtract. Performing this calculation brings us to our final answer. In E, we are given information about the values of the first and second derivatives when t is equal to 1. V dashed of 1 being greater than 0 tells us that the function is increasing at t equal to 1. V double dashed of 1 being less than 0 tells us that the rate of ascent is getting smaller. B is the only graph with these two properties. In part F, we need to find the minimum time required to travel a 10-kilometre distance from A to B without ever exceeding 100 kilometres per hour. To minimise the time, we should travel at exactly 100 kilometres per hour for the entire journey. The time can be found by taking the distance, 10 kilometres, and then dividing by the speed, 100 kilometres per hour. This comes out to be 0.1 hours, which is equal to 6 minutes. In part G, Rowan travels the 10 km distance between A and B. In the first section of his journey, which lasts 2 minutes, he travels at a constant rate of 120 kilometers per hour. This is equivalent to travelling 2 kilometers per minute, so he will cover 4 kilometers in this time. In the second section, he decelerates at a constant rate. We are told that Rowan's average speed is 10 kilometers per hour, and from part F, we know that this leads to a total journey time of 6 minutes. Since the first section lasted 2 minutes, the second section of the journey must last the remaining 4 minutes. The overall distance is 10 kilometers, and since we travelled 4 kilometers in the first section, there's 6 kilometers left over for the second section. So, over the second section of the journey, Rowan has travelled 6 kilometers in 4 minutes. Scaling up by a factor of 15, we can deduce that Rowan has an average speed of 90 kilometers per hour in the second section. He starts at a speed of 120 kilometers per hour, so to end up with an average of 90, he must finish with a speed of 60 kilometers per hour. In other words, his speed decreases by 60 kilometers per hour over a 4-minute period. This corresponds to a deceleration of 15 kilometers per hour per minute. In question 8a, we must find out how much money Olga ends up with 5 years after depositing €3,000 in a bank account. To solve this, we use the compound interest formula. The initial value, P, is 3,000. The interest rate, I, is 2.4%, which is 0.024 as a decimal, and the time period, T, is 5. We get to our answer by using our calculator and then rounding to 2 decimal places. In BI, we must explain what is meant by the present value of a payment of €1,000 in 1 year's time. Simply put, it is the amount of money you will need to invest right now to end up with €1,000 in 1 year's time after adding interest. In BII, Chen ends up with €4,000 in an account after 6 years. We need to figure out the value of the starting investment. We'll use our compound interest formula again. This time, the final value, F, is 4,000. The interest rate, I, is 0.024. And the time period, T, is 6. To find P, we should divide both sides of the equation by 1 plus 0.024 to the power of 6. From here, we use our calculator and round to 2 decimal places. In C, Fiona makes quarterly payments for a loan that has an annual percentage rate of 2.4%. We must find the equivalent quarterly interest rate. It will help to work with concrete numbers, so let's imagine we invest €100 for 1 year. Since there are 4 quarters in a year, after 4 compounding periods, the €100 would grow to €102.40. Putting this into the compound interest formula tells us that 102.40 is equal to 100 times 1 plus I to the power of 4. To solve for I, we divide both sides by 100, simplify the left-hand side with our calculator, take the 4th root of both sides, subtract 1 from both sides, simplify the left-hand side with our calculator, convert to a percentage, and then round to 2 decimal places. In DI, Rowan is making a monthly deposit of €1 into a savings account each month for 36 months. We must express the final amount in terms of a geometric series. The interest rate is 0.11% per month, which is 0.0011 as a decimal. Using the compound interest formula, investing €1 for m months will have a value of A times 1.0011 to the m. The first payment is invested for 36 months, the second payment is invested for 35 months, the third payment is invested for 34 months, and so on. The second last payment will be invested for 2 months, and the last payment will be invested for 1 month. This information can be used to find the final value of each of our payments, and to find our total amount, we simply add together all these values. In part II, we need to find the value of A that will result in having €12,000 in the account after the 36 months. To begin, we set the expression we obtained for the total amount equal to 12,000. Then, we factor out the common factor of A from the right-hand side. Next, we apply the formula for the sum of a geometric series. Here, the first term, A, is 1.0011, the common ratio, R, is 1.0011, and the number of terms, N, is 36. From here, we divide both sides by the value of this sum, then use our calculator and round off to get our final answer. In E, a park sells 3 types of ticket. We are given the expected value of the price of a ticket, and we must use this to find out X, the price of an adult ticket. To find an expected value, we begin by multiplying each price by the corresponding percentage. For the child ticket, we get 11 times 52%. For the student, we get X minus 5 times 15%. And for the adult, we get X times 33%. The expected value is equal to the sum of these 3 terms. We can rewrite the percentages as decimals, multiply out the brackets, combine like terms, subtract 4.97 from both sides, and then divide both sides by 0.48. This tells us that X is equal to €18.50. In part F, we are told that a shop sells an item for a margin of 18%, and we must find the markup. It's useful here to work with concrete numbers, so let's assume that the selling price was €100. The margin being 18% implies that the profit would be €18. The cost price is the selling price minus the profit, which comes out as €82. To find the markup, we divide the profit, 18, by the cost price, 82. Written as a percentage, correct to the nearest percent, we get a final answer of 22%. In question 9AI, we must list the factors of 2 to the power of 4. 2 to the 4 is equal to 16, and the factors of 16 are 1, 2, 4, 8, and 16. Notably, these can be expressed as all the integer powers of 2 from 0 to 4. In II, we must work out how many factors 3 to the power of 7 has. Well, the factors will simply be the integer powers of 3 from 0 to 7. Hence, 3 to the 7 has 8 factors. In III, we need to determine the number of factors for 2 to the 10 times 3 to the 12. Each factor will be in the form 2 to the a times 3 to the b, where a is an integer between 0 and 10, and b is an integer between 0 and 12. We have 11 choices for a, and 13 choices for b. Hence, there will be 11 times 13 different ways to pair an a value with a b value. This means that we'll have 11 times 13, which is 143, different factors. In BI, we must list all the x-y pairs such that x times y is equal to 12. The ordered pairs are 1 times 12, 2 times 6, 3 times 4, 4 times 3, 6 times 2, and 12 times 1. In parts II and III, all we have to do is plot these 6 points on the given diagram, and then join them as best we can with a smooth curve. In CI, we must find the equation of the tangent to the curve at the point P, 12 over P. To use the equation of the line formula, there's 2 things we need to know: a point on the line and the slope. The point is given to us directly here. To find the slope, we differentiate our function y is equal to 12 over x, and then sub in x equal to p. Now we can use the equation of the line formula. x1 is equal to p, y1 is equal to 12 over p, and m is equal to minus 12 over p squared. We multiply out the brackets on the right, simplify, add 12p to both sides, and simplify again. In CII, we must find the area of a shaded region in the given diagram. The area forms a triangle, and the area of a triangle is equal to a half times the base times the perpendicular height. The length of the base is equal to the x-intercept of our line. To find this, we sub in y equal to 0 and then solve for x. To do this, we subtract 24 over p from both sides, multiply both sides by p squared, simplify, and divide both sides by minus 12. This tells us that x, the length of our base, is 2p. The perpendicular height of the triangle corresponds to the y-intercept of our line. To find this, we let x equal to 0. Calculating the right-hand side tells us that y, the perpendicular height, is 24 over p. We get our final answer by subbing these values into the area of a triangle formula and simplifying. In question 10a, we are given the first three terms in a sequence of rectangles and must draw the fourth term. The first term has one rectangle, the second has two rectangles, and the third has three rectangles. Continuing the pattern, the fourth term will contain four rectangles. The height of the triangle, which is 8 units, is equally split over the four rectangles, so each one will have a height of 2 units. In B, we must find the total area of the three rectangles in the third term. The triangle is 8 units tall, and this is evenly split among the three rectangles, so each rectangle will have a height of 8/3 units. The width of the triangle grows from 0 units at the top to 2 units at the bottom. Since the width grows at a constant rate, the growth in the width over each of the rectangles will be the same, 2/3 units. This tells us that the top rectangle has a width of 2/3, the middle rectangle has a width of 4/3, and the bottom rectangle has a width of 6/3, which is equal to 2. Now, we can find the area of each rectangle by multiplying the height by the width. To find our total area, we simply add these results together. In part C, we must find the total area of the n rectangles in Tn. We can do this by generalizing the argument from part B. The total height of the triangle, 8 units, is split evenly among the n rectangles, which means each rectangle will have a height of 8/n. The width of the triangle grows from 0 units at the top to 2 units at the bottom. Since the width increases at a steady rate, the increase of width between successive rectangles will be 2/n. In other words, the widths of the rectangles will be 2/n, 4/n, 6/n, all the way up to 2n/n. Multiplying each of the rectangle widths by the common rectangle height, 8/n, gives us the areas of the rectangles. Adding these together gives us the total area. From here, we can factor out the common 8/n, and then factor out another 1/n. To calculate the expression inside the brackets, we can use the formula for the sum of an arithmetic sequence. The number of terms, n, is equal to n. The first term, a, is equal to 2, and the common difference, d, is equal to 2. When we sub in and simplify, we get n times 2 plus 2n all over 2. We can write this expression in for the sum we had, and then simplify to get our final answer. In part D, we're given an expression for an and asked to find the first value of n for which an is greater than 95% of the area of our triangle. The area of a triangle is equal to 1/2 times the base times the perpendicular height. For our triangle, this comes out as 1/2 times 2 times 8, which is 8. To find 95% of the area, we multiply 8 by 95%, which gives us 7.6. We need an, which equals 8 times n minus 1 all over n, to be greater than this value. We can solve this inequality to find the value of n. We multiply both sides by n, multiply the brackets on the left, subtract 7.6n from both sides, simplify, and then divide both sides by 0.4. N is an integer, and n must be strictly greater than 20. the smallest value of n which satisfies these conditions is n is equal to 21. In part E, we must find the volume of a pyramid in terms of the constants c and h. We're given an expression for the volume. It's the integral from 0 to h of s of x. So the question simply boils down to calculating this integral. We're told that s of x is equal to x squared times c squared over h squared. C and h are both constants, so the multiplicative constant, c squared over h squared, can be brought outside the integral sign. X squared integrates to x cubed over 3. We sub in the upper limit, h, sub in the lower limit, 0, and then subtract. We simplify, and then observe that h cubed divided by h squared is equal to h. This brings us to our final answer. In EII, we must find the rate of change of s with respect to time when x is half the perpendicular height of the pyramid. In terms of derivatives, this corresponds to evaluating ds dt at x equal to h over 2. We can solve this using related rates. The derivative we want, ds dt, can be written as the product of ds dx and dx dt. We are told that x increases at a rate of 3 units per second, so the rate of change, dx dt, is equal to 3. S of x was defined to be x squared times c squared over h squared. Differentiating this expression and simplifying tells us that ds dx is 2xc squared over h squared. ds dt is the product of these two derivatives, which comes out as 6xc squared over h squared. We want the rate of change when x is half the perpendicular height of the pyramid, so we should sub in x equals h over 2. Cancelling the h in the numerator with one of the h's in the denominator brings us to our final answer of 3c squared over h square units per second.